Alright, what's going on, everyone? Mr. D'Souza here. I'm actually really excited that I get to do a video for all of you. So we're going to be doing the practice problems for the exponential growth and decay that you learned this Tuesday. Also, my cat's just chilling right here. Hopefully my microphone doesn't pick up his purring, and hopefully he doesn't destroy everything. Anywho, we're just going to jump right into it. Make sure that you're editing your work. Make sure you're using either a calculator or you can use a phone. Either one is going to be helpful and it's going to work. So let's just jump into it. So the first thing that we're going to do is we're going to review a couple of things. So in general, you're learning about something called exponential growth. It's another type of function that can describe certain scenarios. So for example, when we learned about linear functions, we learned how things could be at a steady increase. Like, for example, a flower growing 1 centimeter every month or something like that. Something that has a constant rate of change. Now, for exponential growth and decay, well, that can actually model other things. So I know Ms. Fu talked about like virus spread, people getting sick, but also it really does explain different phenomena that happens in the real world that you're eventually going to get to. So don't worry about that. If anything, I think it's probably one of the cooler functions that you learn in high school because it talks about more things that you personally see in your real life. So let's go over two of the facts. So the first thing that you learned is what exponential growth is. All right, so exponential growth, just like when you learned linear functions, right? Y equals mx plus b, all those letters represented something. For exponential growth, we have a similar function, a equals p times, hi Riley, a equals p times 1 plus r to the t. Right? So this happens to be exponential growth, mainly because you have this 1 plus, okay? Because your rate, if it's greater than 1, it's going to be, increasing. We'll get there, don't worry. And then we also have what A, P, R, and T are. So A is the final amount after you calculated something changing over time. P is the initial amount. We use the letter P because that refers to principal. You're going to see this in other parts of mathematics. R is the rate, how things are changing. So it could be changing positively, so up, like greatly, or negatively, so down, decreasing. And then most importantly is the time period. Over how many years or how many days or months is this changing, right? So you learned about that. And then you also learned about, oh, hey, Ms. Fu, what's up? You also learned about exponential decay, which is the same thing, only a little bit different. So our rate is calculated. It's 1 minus r. So when it's 1 minus, right, that means that your decay factor is between 0 and 1. And you'll explore a lot of this more when you start graphing why this works. But when your decay factor is between, hi Riley, 0 and 1, it's going to wind up exponentially decaying. So, all right. So we're going to jump into the practice problems. Let's do it. All right, so we're going to go through the first example together so you can see a bunch of equations on the left-hand side, and we're going to try to fill out this chart the best way we can. I also put down that review little part, that little section that's like super important because that's going to help us answer all these questions. So first, the first column after the equation column, we're going to decide if this is a growth or decay. Okay, so remember, growth is when your growth factor is greater than 1, right? So this entire thing inside the parentheses is your growth factor. So one way we can do this is just add those numbers. If that number that you get is greater than 1, awesome, it is growth. Or you can also look that it says 1 plus, which you can see directly from the equation or the formula, if you want to say it like that, is growth. So I'm going to put a G for growth. The next one is similar, right? It says 1 minus. Well, exponential decay, the growth factor has 1 minus the rate. Or another way you can do that is literally do 1 minus 0.02, and you will see that you'll have a number less than 1 but greater than 0. And according to the fact that you learned, that if your decay factor is between 0 and 1, well, it'll be exponential decay. So I'm going to put a D for decay. All right, so the next two look a little bit different, right? They already combined the 1 plus the rate, or the 1 minus the rate. But just go back to the fact. If your growth factor is bigger than 1, awesome, it's exponential growth. If it's between 0 and 1, then it's exponential decay. So our growth factor here is 0.65. Is that bigger than 1, or is it in between 0 and 1? It's in between 0 and 1, so it must be exponential decay. Okay, and then the next rate is 1.05. Well, is that bigger than 1, or is it in between 0 and 1? Yeah, it's bigger than 1, so that means that must be growth. Awesome. Okay. Challenge question, and this is something that I just want you to think about. It has nothing to do with this question. What if the growth factor was equal to 1? Or what happens if the growth factor is 0? You're going to explore that in the future, but think about it. But for now, we're only talking about growth factor being bigger than 1 or in between 0 and 1. All right, so the rate. So the rate is R. So if you look at our equations, it's this number, right? But we need it as a percent, okay? So if you look over here, I'm going to actually erase some of this so that we have more space and more, it's a little bit more organized. Let's do it in green because that is the best color. The rate is right here, 0.3. However, we want it as a percent. So how do we go from decimal to percent? Yeah, so if you remember in the video, Miss Fu said you just move the decimal place over to the right 2 spaces if you want to make it percent. So I'm going to do that. So 1, 2, this is my new decimal place. And since I have a space here, I got to fill it with a 0. So this is the same thing as saying 30%. Let's do the next one. So you can identify that the rate is 0.02. Again, if we want to make that percent, we move that decimal place over twice to the right. All right, so we got 2%. Now the next one is a little different. Our rate is not really here. That's the growth factor. But remember, we can figure out what the rate is. We know that this is hi, Riley. We know that this is the decay. This is exponential decay. We know that exponential decay, the growth factor is 1 minus R. And that should equal 0.65. Okay? Now, if I wanted to solve for R, I'm going to use inverse operations. I'm going to move the 1 to the other side by subtracting 1, and then I'm going to multiply both sides by -1. So I got that my rate is 0.35. However, we need to write it as a percent. So if we're going from decimal to percent, we're going to move our decimal place over twice. Okay, and it's 35%. My cat is just chilling right here. Hi. All right. Okay, cool. So let's do the last one. So the last one, we know that this is exponential growth. We said that. So we know that 1 plus R is equal to 1.05. All right, so now we just got to solve for R. So I'm just going to subtract 1 on both sides, and let's see what we get. All right, so now we have it as a decimal, but we want it as a percent. So to go from a decimal to a percent, all you need to do is move the decimal place over 2 times to the right. And the rate is 5%. All right, so let's do the initial amounts. Let's do it in pink. All right, so the initial amount, if we look at over here, we know that the initial amount is the same thing as the principal, which is P, which is really the coefficient of the growth factor. So if this whole thing in parentheses is my growth factor, the initial amount is the number that's the coefficient of that. So it's the number next to it. So we got 1,200, we got 55, we got 5,575, and we also have 2,000. Okay, last but not least, the time period. Now, in these examples, we're just given t. But that could change based on the problem, based on what you're trying to model. It's based on a lot of different things. But for now, our time period is just t. All right, so take a second to make sure you copied all this down, edit your work, and then let's just move on. Sick. All right, so we're going to do this problem together. The population of Henderson City, I don't know where that is, was 3,381,000 in 1994. And, oh, that's a great year, and is growing at an annual rate of 1.8%. If this growth rate continues, what will the approximate population of Henderson City be in the year 2000? So, just like what was said in Ms. Fu's video, there are 4 things you gotta do. Identify if it's growth or decay. Oh, my hit buttons! Identify the growth or decay. Identify the parts needed for the equation, A, P, R, and T. Convert the rate to a decimal, and solve. Okay? So, first things first, is this growth or decay? So let's check this out. Is there anywhere here in this question that says growth? Yeah, it says it's growing at an annual rate. So we know it's growth, therefore we know it's going to be this formula. Sick. So now we just need A, P, R, and T, or rather, we got to fill in as many pieces as we can. My cat's literally watching my mouse move on the screen. This is not going to be good if he decides to do something crazy. So, we are trying to figure out what the approximate population of Henderson City will be in the year 2000. So that means we're trying to use an equation to figure out something in the future. So that means we're actually looking for A. So P stands for principal, the initial amount. It says here, that the population of Henderson City was 3381000. So that's what it is currently, initially. So that's going to be P. Now, we got to figure out the rate. Now, the rate is 1.8%. However, when we use the equation, when we are going to be substituting numbers into the equation, you can't use percent. You got to convert it to a decimal. So it's the opposite of what we did. So from going from a percent to a decimal, you're going to move your decimal place over to the left 2 spaces. Okay? Now, T stands for time. So we need to know how much time in years is this going to take place? Well, we started in 1994, and we want to figure out what the approximate population will be in the year 2000. So how many years is that? 6. So T is going to be 6. Now, all we got to do is substitute all of these numbers into the following equation and solve for A. So let's do that now. All right, cool, I fixed it. So all I did was substitute in my P, my R, and my T, and now I'm just going to use my calculator. Now, you can use a calculator if you have one. If not, totally cool. You can definitely use your phone. You can also find calculators online. If you still did not use the calculator that we posted, send us an email. We'll send you the calculator again that you can use online. So I'm just literally going to put this in my calculator. All right, and then I got that my answer is going to be the following. It's going to be 3,70629. Hold on, 37629. Okay. Now remember, this represents population. You can't have, let's see, boom, boom, 3,762,979.382 people. That doesn't make sense. So we got to round down in this case. And this is almost identical to what you did in the mini lesson. I'm pretty sure the word people got cut off. I'm sorry if it did. Super important. We're doing real life stuff. Does this make sense? We started with 3,300,000 and something people in 1994. And we're saying that we're going to have some kind of growth in the next 6 years. So is it possible that we go from 3,300,000 and something thousand to 3,700,000 and something thousand? Yeah, the answer is yes. Now, if you wound up getting an answer that said like 2 million people after 6 years, that should be red flags because in the question it says it's a growing annual rate. So we would expect our answer should be bigger than the initial amount. So a lot of these questions that you're going to be doing, ask yourself, does my answer make sense? Let's do the last question together. Awesome. So this is a two-parter question. Jacob and Jessica are studying the spread of dandelions. Jacob discovers that the growth over T weeks can be defined as the following function. F of t equals 8 times 2 to the t power. Jessica finds that her growth function over t weeks is g of t equals 2 to the t plus 3. Now, these exponential functions, these growth functions, do look a little bit different. However, let's use algebra that we already know to connect what we've learned in the past to what you learned in this lesson about growth. Okay? So this says calculate the number of dandelions that Jacob and Jessica each will have after 5 weeks. So that means that in this function, t is our variable. Let's do this first one. So we're going to calculate f of 5. And remember, we're just substituting in 5 where we see t. So we have 8 times 2 to the 5th power. Now I'm going to use that on my calculator. 8 times 2 to the 5th power is 256. And we know that that's dandelions. Now let's do Jessica's. Jessica's growth function was g of t. So again, if we're going to calculate g of t, we want to know after 5 weeks. So g of 5, let's see what happens. G of 5 is equal to 2 to the, g of 5 is equal to 2. Well, t is 5, so we're going to do 5 plus 3. I just want to double check and make sure, yes, it is plus 3. And let's see what that is. So that's the same thing as saying 2 to the 8th power, right? Because 5 plus 3 is 8. So 2 to the 8th power is 256 as well. Interesting. Based on the growth of both functions, explain the relationship between f of x and g of t. Oh, sorry, f of t and g of t. My mistake. So off the bat, if you just tested when t is 5, you see that they get the same answer. Now there's a couple of things that you can do. You could say that yes, both functions wind up being the same thing, but you only tested one thing. Something else that you can do that I know you're going to be doing in the very near future is you can just graph it. So I'm going to use my calculator. I know in the future you'll be seeing other apps that you can actually use either on your phone or online that you can use. But if I type in, actually I can do it, I'm not going to do it there. I'm going to do it right here. If I type in 8 times 2 to the x power And then I also type in the other function, which is 2 to the t plus 3 power. And I graph it on my graphing calculator. Should have done it on my computer. I apologize, but it's okay. You wind up getting graphs that overlap, which means that they're the same. But I'm going to show you mathematically why it is. And you got to remember some of your exponent rules. So come along this ride with me. Okay? You're going to actually be doing a lot more of learning how to do a lot of this algebra manipulation, is at least how I like to call it. But check this out. So the first function is f of t equals 8 times, so 8 is going to be in parentheses because we don't want it to mingle with the exponents. So 2 to the t power. Now, there are no algebra rules. Actually, there are, but by looking at this, there really is nothing that we can do with this. However, if we check out g of t looks like this. Okay, so the rule that you've learned, whether if it was in our class or in middle school, you've definitely seen this before. If you have something raised to a sum, this is the same thing as saying 2 to the t times 2 to the third power. But let me ask you, what is 2 to the third power? 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So this becomes 8. I can't do anything with my 2 to the t power, so I'm going to rewrite it down here. Okay? And this happens to be another way that you can write g of t. So my question for you is, what do you notice about g of t and f of t? They're the same. So Jacob and Jessica literally have the same function. It's just written in 2 different ways. And the way that we can show that they are the same is by doing a little bit of algebra manipulation, changing some things around so that it's the same thing, just written a little bit differently. And you can actually see that they are literally the same. All right, so I hope this was helpful. Again, if you have questions, comments, concerns, if you didn't understand something that I said, or you still have a question about the video that Ms. Fu posted, or anything at all, please reach out. Remember, math is fun, and I hope to talk to all of you soon. Have a great rest of your day. Bye, everyone.